All right, good morning, everyone. Happy St. Patrick's Day. Yes, it is my birthday, so
Yay.
my family likes to call this my birthday suit. So it does have matching pants. So yeah. Um, thanks for the birthday wishes. So all right, let me share my screen. Wrong screen. Here we go. Right. So yes, today is March 17th. Today is St. Patrick's Day. So today we're going to be looking at the Chapter 8 project. So exploring a sampling distribution. Um, so don't forget that next week, Tuesday, we're going to be doing our candy project. So you need to go out and purchase some candy. You need a bag of M&Ms and a bag of Skittles. Okay, somewhere between somewhere more than so like 3 ounces or more. So 3 ounces or more, up to like maybe 16 ounces. You can get more if you want, but uh so we talked about that. I think that's it. Once again, I'm behind on grading. It's always happens. But if there ever does happen to be a assignment that you're like, I really want to know how I did on this because I need it for if I need it for studying, then reach out to me, let me know. Okay. Montez, note today is not the candy project. We're going to be using that on the 24th. So maybe I gave you a little bit too much notice, so I apologize for that. So don't eat it for a week. Okay. Um, all right. So uh, the yeah, the Chapter 8 project is about sampling distributions and about the central limit theorem. Okay. So we're going to go to Canvas and we're going to click on the Chapter 8 project. And there are two links that you'll need. The first is the Google document, which is where you're going to put all your answers in. So I will drop that in the chat for you. And the other one is a link to StatCrunch. It is a sampling distribution applet. So again, I will drop the link in the chat for you for that one as well. So there's that. I don't think you need to sign into StatCrunch to use this one. So I think you can just go to town on it. So anyway, but let's start with our Google document and we'll hit File, make a copy. And I'm going to save this. Where am I saving this? I'm going to save this in my Spring folder here. Oh, I'm going to change the name of it because it's not, because it's Spring 2026. And there we go. All right. Right. Um, all right. So we're going to load the sampling distribution bell shape applet. So there's a link here as well, but I already gave you the link that was in Canvas. Set the applet so the population is bell-shaped, copy and paste the mean, median, and standard deviation. Okay. So here's the idea for this project. Okay. Um, so part one is there's what is there? There's part two, part three, and then part four. Okay. So there's four parts to this project. So I want to talk about the whole thing all at once first. So the central limit theorem is an important theorem in statistics. I mean, obviously, it's the central theorem. It's center of everything. It's important. Okay, kind of like the Pythagorean theorem is one of the most important theorems in geometry. Okay, um, and what it does is it says that uh, if your sample size is large enough, okay, then the distribution of means of samples um, ends up in a normal curve. Okay. So that sounds confusing. Okay. And it is. It's a little bit confusing. The same way that like when you first learn the Pythagorean theorem, you have to learn about like squares and square roots and right triangles and all that kind of different stuff. Okay. Um, so basically what we're getting at is it doesn't matter what shape your distribution is. It can be normal, it can be skewed, okay? But if you take a sample and then take another sample and then take another sample, you keep taking samples over and over. The and then you look at the means of all those samples, the distribution of those means will end up in a normal shape regardless of what your original population looked like, okay? We're going to explore that today. So if it's still confusing to you, don't worry about it, okay? But part one, we are going to be looking at a normal distribution. So this population right here is already a normal distribution. I find part one boring because if you take samples from this population, you would expect that if you then graph the distribution of the samples, it would also be normal. It's kind of obvious. Okay. So part two is where the exciting part is because we'll start with a skewed right. Part three is exactly the same. You'll do a skewed left distribution. And what you'll find is as your sample size increases, your the distribution of sample means becomes normal. Okay. Becomes closer and closer to normal. Okay. Um, anyway, and then part four is just like a recap. Okay. So anyway, follow along with me on this and you'll be fine. Okay. So part one, question one, uh, set the applet so the population is bell-shaped. Well, it already is. Copy and paste the mean, median, and standard deviation. Okay. So they give you the mean, median, and the standard deviation up here in the upper right. So that's what we're going to use. 25, 25, and 5. Okay, those are our answers for this first part. Oops, what did I do? 25. Okay. All right. Obtain 1,000 random samples of size 2. Copy and paste the values of the mean standard deviation into the table below. Describe the shape of the distribution of sample means. Is it very skewed left, very skewed right, slightly skewed left, slightly skewed right, or normal? Repeat the process for the other sample sizes given. All right. So what is this applet? So this distribution at the top is our population. Okay. It is like, when we had when we were looking at home runs, right? There were like 6,000 home runs, and you could make a histogram, and the histogram had this shape to it. It was symmetric. It was normal. Okay. This one's much more normal than the one that we had because we had real data. Real data is always a little messy. Okay. But you can imagine that this population, it could also be like the heights of all the people in the US. Okay. That height histogram is going to look very much like a normal curve. Okay. So when we are looking at a population, usually the population is huge, okay? I can't measure every person in the US, their heights, and put it on a histogram because there's millions of people. There's hundreds of millions of people in the US, okay? And it's going to take way too long to gather all that data, okay? Or if I wanted to do everyone in the world, right? There's people that, don't even have contact with outsiders, right? So I can't necessarily measure everyone. Okay. So we take a sample. Okay. And the sample is random. Okay. We've talked about a little bit about how to select samples. We'll talk a lot more in this chapter and later chapters. Um, so that's what this lets you do is it lets you take a sample from this population. Okay. Now you can set your sample size over here to whatever you want. Okay. We're going to start with a sample size of 2. Okay. So you don't need to click on this stuff yet. But if I click up here in the upper left where it says one time, it'll select one sample for me. There it is. I selected two people, and then I took the average of their heights, or whatever it is I'm measuring, and dropped it down here in this green area. Okay, so this down here is measuring the average of my sample. If I click that one time again, I'll get a different sample. This time I got a result way over here. Okay, and you could keep clicking on this, selecting two people at a time, and you'll keep getting different different people selected, and then you take their average and you get another green point down here. Now, the question asked us, obtain 1,000 random samples of size 2. So my size is 2, and I've been clicking one at a time. I don't want to have to click this 1,000 times, okay? Um, Luckily, there's a 1,000 time button right here. You could do it 5 times, right? So there's a sample, right? And it'll, but that's still going to take us forever. We wanted 1,000, right? So let's hit reset at the top. All right, so we're back to our start, okay? And we'll just hit this 1,000 times. Okay. Now it's not actually going to show you all of the samples that it took. This middle one is just an example sample. Like you saw a second ago, when I hit one time, it selected two people, two of the points in my gray my gray population. So this is just happens to be the last sample that it took. Okay. But down here are 1,000 green dots that it's selected the samples for us, and then taken the average of each of those two people in the sample and put that average into this bottom graph. Okay. So uh, I'll say again what I need you to do. I need you to hit reset so that everything's blank, and then hit 1,000 times, and that's it. Okay. And then over here on the right, we're going to record the mean, median, and standard deviation into our project. Okay, so let me see if I can make my project a little smaller. There we go. Okay, so for part 1B, my sample size is 2, n is 2, and the mean that I got was this number right here, 24.94. Okay. Now you're going to have a different number than mine, okay? But it's going to be close-ish, okay? That's okay. Part of the fun of the projects is you get to use your own data. You get to follow along yourself. So your number should be different from mine, okay? So don't just copy what I have. My standard deviation was 3.45. I'm just going to do 2 decimals, okay? You can do 3 if you want. I don't think it says how many, yeah, I don't see. All right. Oh, I put that in the wrong spot. Okay. The shape, I need to put, yeah, if you got, that sounds good, well done. If you got 24.8 or 25.1, 25.2, all of your means should be hovering somewhere around 25. Okay. So not exactly 25, but you probably got some kind of decimal. Okay. So, yep, that sounds great. What'd you get for standard deviation? Did you get somewhere around 3.4, 3.5, 3.3? What did you guys get? 3.5, 3.45, 3.7. Okay. Those all sound great. Okay. Those all sound excellent. Okay. So lastly, I need to describe the shape of my distribution. Now, not the shape of the original one. The original one was a normal curve, okay? We need to describe the shape of the green distribution down here. This distribution down here is called the distribution of sample means. I took a bunch of samples, I took their means, and I plotted those on this graph, this green graph. So do you think this is skewed left, skewed right, very skewed left, very skewed right, or normal? What do you guys think? take a look at your graphs. What do you think? That one I want. This one. Is it very skewed left, very slightly skewed left, very skewed right, slightly skewed right, or normal? What do you guys think? Yeah, Caleb says normal. Yeah, this is a pretty boring result. Your original population was normal. You took a bunch of samples and you got a normal distribution. That is not a surprise. Okay. So anyway, but we'll see. We're gonna push forward with part still on 1B, but now what we're gonna do is we're gonna change the sample size to 5. Okay. So, all right, leave your population alone. Okay. But the middle box right here, you're gonna change this to a 5. Okay. And it'll reset all of the things. Okay. Or you can hit the reset button up here. Either way is fine. If you do hit the reset button up here, then yeah, okay, I think we're good. Um, uh, you don't need to do a single sample, but if I do a single sample, what it's doing now is it's selecting 5 people from the gray population and then taking the mean, taking the average of those 5 people. Okay, so that's what happened here. Okay, and then if I did another 5 people and then take their average, right? So it's doing the same thing. All that's different is I'm doing a bigger sample size. Okay. Still taking their average, plotting it in green down here. I'll hit reset. So make sure your mean is 25, median is 25, standard deviation is 5, sample size is 5. Hit 1,000 times, and there is our result. Okay. Down here is the distribution of sample means. Okay. And we're going to write down again our mean, our standard deviation, and our shape. Okay. So not the population mean and standard deviation. Those didn't change. Okay. The one down here, the sample mean. So my mean now is 25.01. My standard deviation is 2.18. Okay. Uh, and then what do you guys think about the shape? Still normal? Everyone agree? Yeah. Still looks like a bell to me. It's a little funky, right? And that's because the samples that were taken were random. Okay. So sometimes you pick people who are really tall, really short. I mean, I'm not sure what this population is, but maybe we go with like maybe we go with like how much people weigh. That weight population shape is going to be normal. And so, like, if you take a random sample, sometimes you get people that are heavier, sometimes you get people that are lighter. Like this sample right here looks like I picked people randomly that were maybe above average. Okay. So, anyway, but it's roughly normal. Okay. Uh, And you can see that it's symmetric because if you look at the mean and the median for the sample means, they're very close, 25.01, 25.06. We said that when your mean and your median are close-ish, that it's symmetric, okay? They don't have to be equal for it to be symmetric, but all right, we got to do this again for 10. So change your sample size to 10 right here on the right. Hit reset 1,000 times. Now we're just gonna keep booking along. For when my sample size is 10, I get an average of 25.09. Oh, I gotta round that up. 25.10. Uh, Standard deviation 1.56. Is it still normal? Yeah, it's still normal. And now I gotta do it at 30. So sample size of 30. That's a pretty cool shape in the middle there. So 30 gray dots selected from my population. I get 25.05, standard deviation 0.9. 2, and normal. Okay. And obviously you guys are going to get different numbers from me, but your shapes are all pretty much going to be normal. Okay. All right. Part 1C. For this bell-shaped population, as sample size increases, so we kept bumping our sample size up by a little bit over and over and over. The mean of the sampling distributions of sample means appears to what? Decrease, stay the same, increase. So the means. So my first mean was 24.9, then it was 25.1, then it was 25.10, 25.05. These mine are increasing, but not increasing significantly. Take a look at your means. What do you think the answer is for 1C? Are they going up? They're going down? Staying the same. Yeah. Caleb says the same. I agree. So, I don't have a way to circle this, so I'm just going to highlight it in yellow, or you can do a fancy color if you want. Oh, today is St. Patrick's Day. I'm doing green. I'm doing green, guys. Okay. 1D. For this bell-shaped population, as sample size increases, what happens to your standard deviation? So these are my standard deviations. So take a look at yours. Mine went from 3.4 to 2.1 to 1.5 and down to 0.9. So what do you guys think? Increase, decrease, or stay the same? Yeah. Decreased significantly. Did it decrease significantly? Well, it went from 3.4 down to 0.9. 0.9 is 3 times smaller than 3.45. So yeah, it definitely decreased significantly. 3 times smaller is quite a bit smaller. All right, for this bell-shaped population, how does sample size appear to affect the shape? So we looked at the means. Those all stayed the same. Standard deviations, those went down, and the shape stayed the same, right? How does the shape sample size appear to affect the shape? Sam, uh, as sample size increases, the shape stays normal. All right. I had said I find part 1 boring, and that was boring. So let's go on to something very exciting, part 2. Uh, Draw a very skewed right distribution on the applet by holding the left mouse button down and dragging the mouse over the distribution. Note the mean and the median need to be at least 2 points apart. Okay, so let's go back over to our uh, let's go back over to our population. So if you click on this uh, population here, you can make it look however you want it to look. You can make some kind of crazy shapes, okay? We are trying to make something very skewed right, okay? So to make it skewed right, I need like a big bump over here on the right, okay? And then I need like a tail that goes off to the right. And if you make yourself like a really long tail like that, your mean and your median should be really far apart. So yeah, maybe I'll even make my tail a little bit bigger over here just to give myself some outliers, right? So I need my mean and my median to be at least 2 apart from each other in order for it to be very skewed right. So my mean in this case is 12.6. My median is 10.3. That's a difference of 2.3. So maybe I can make my, so that's good. if that's what you guys have. Maybe I'll make it even more skewed to the right.
It's surprising that it takes so much skewing to just get it two apart.
Yeah, it does. Oh, now I'm three apart. All right. Well, you don't need to be that. Yeah, so just two apart's good. So, um, okay. So there is my uh population. Okay. Um, so this population would is non-normal. Okay. It's not symmetric. It is skewed right. Yes. So this could represent like average annual income or the prices of houses or something like that, where you're going to have most people are down here in this area. Um, you have a couple people who are, only that are unemployed. They're making zero. But you got a couple of millionaires up here who make tons of money, right? You got some outliers. Okay. So if I select a sample from this, I'm going to expect that my sample is skewed right. So we're going to reset our sample size back to 2. So over here on the right, reset that to 2. And this project's a bit redundant, but we're going to be copying the same kind of things. Okay. So part 2 is very much like part 1. Um, but we're going to see something interesting. So first of all, our mean. My mean is 13.00, but yours will probably be different. So put yours in, whatever you have. My 10.9, well, 10.10 because I gotta round that up. Standard deviation, my standard deviation is 8.13. My standard deviation is huge, right? When you have skewed, it's very spread out, get a bit much bigger standard deviation. Okay. Yours is your numbers will be different. That's totally fine. Um, so obtain 1,000 random samples of size 2 and paste the values, the mean, standard deviation, and the shape here. Okay. Repeat the process. So it's the exact same thing that we did for part 1. Okay. But I want to pause here for a second. I want to hear some guesses. So if I do this, if I do these means with size 2, okay, um, each time I take a sample, I do the average, and you can see that the average is the number right in the middle. So that's why the green dot landed here, right? If I do a sample here, whoa, I got an outlier. So uh, this average is going to be way up here. Okay. If I keep doing this 1,000 times, what shape do you think my green dots down here at the bottom will be? I haven't done it yet, but I want to hear a guess. Do you think it's going to be skewed or do you think it's not going to be skewed? If my population is skewed right, I I agree with you guys. Nicole, Caleb, I agree. I would bet that my sample means distribution down here is also going to be skewed. Okay. So that's a boring result, just like when we had something that was normal and then the bottom one ended up being normal, right? So let's actually do it. Make sure you set your sample size to 2, click on 1,000 times, and let's write down our mean, our standard deviation, and our shape. So if I mean this time, 12.71. Standard deviation is 10.59. And my shape. Well, taking a look at my green distribution down here, I agree with you guys. It is skewed right. Now, the question is asking, well, don't just say if it's skewed right. Is it very skewed right or slightly skewed right? Um, I think it is very skewed right. My mean and my median are still 2 apart. So maybe yours aren't, but I still have a huge tail out here. Okay, so very skewed right. Okay. If I change my sample size to 5, so you're gonna go to the middle number, change it to 5, do 1,000 times, and we'll record that information. So 12.94 and 3.51, and let's see, shape. So still skewed right. Would you call this very skewed right or slightly skewed right? Or medium skewed right? I don't think that's a term. Caleb says slightly. Agree, same answers, different answers. I'll go with you, Caleb. That's fine.
I like
Um,
medium.
medium skewed right, slightly skewed right. Okay. And we'll do 10. We're just trucking along right. And we'll write down our shape. So our mean and shape. So 12 point, mine's 12.99. Standard deviation 2.5. 1. I want to pause here. So I do still have some outliers. I do still think this is skewed right, slightly skewed right. Okay. But something weird's happening. Slightly skewed right. The shape, the original, so when we were at 2, it was still very skewed right. We keep bumping our sample size up. The next one's going to be 30. And what's weird that's happening is our distribution, even though our original population was extremely skewed right, when we run this at 30 and we run it 1,000 times, our sample means distribution is not skewed anymore. Okay. Maybe it's a little bit. Okay. But it's getting it's getting less and less skewed. And that is an exciting result. All right. So let's finish filling this out. 30, 13.03. Standard deviation 1.49, and my shape. Okay. What do you guys think about this shape? Skewed right, very skewed right, slightly skewed right, or normal. It doesn't have to be perfectly normal for it to be normal. We've said that already. I think this looks normal to me. Okay. And actually, we don't need to, but if you kept going with your sample sizes and you went up to like 50 or 70 or 100, okay, and you ran that, it's going to be more and more normal as you go. Okay. So, um, the bigger your sample size, the closer this sample means distribution is going to get to normal. Okay. And why that's an exciting result is because, well, first of all, it's unexpected. I said a second ago, if our population is super skewed right, then it makes sense to me that when you take samples and you look at those means, that the result of that is still going to be skewed right. Okay. So it's counterintuitive. Okay. But also, since it's normal, that means we can use all of the chapter 7 stuff that we learned about the normal distribution on it. So we can look at what percent of the time it's going to be above or below this value, right? We looked at z-scores or x-scores. We can use all of that information, that calculator. Okay. We can also do a lot of stuff that we're going to talk about in chapter 9 and 10, where we build confidence intervals and we do hypothesis testing. All of that stuff is built around the fact that the central limit theorem is happening. Okay, is true. Okay. So maybe you're not excited about it. I'm excited about it, but I'm excited about math. So, when you learn the Pythagorean theorem, you're not like, oh my God, that's so amazing, right? But I mean, been around for thousands of years. But anyway, this is the central limit theorem, which is that as your sample size increases, if you get to the right sample size, you can treat your sample distribution as normal. Okay. Now, So at 30 is when we started to see that it was normal, right? And 30 is going to be our cutoff. 30 is going to be what the central limit theorem says. You want to make sure your sample size is bigger than, okay? So I can't just take two people because that was still skewed, okay? The bigger your sample size, the more accurate you will get, but 30 is kind of the cutoff, okay? Just like with the Pythagorean theorem or other theorems in mathematics, there are requirements around it. Like when you talk about a squared plus b squared equals c squared, that only applies to right triangles. Okay. And this central limit theorem that we're talking about only applies to samples that are 30 or more. Okay. But as long as you have that, as long as you have a right triangle, you can use that formula. As long as you have a sample that's bigger than 30, then you can use that normal, all of that normal calculator stuff that we learned, right? Stat calculators normal in StatCrunch. All right. Moving on, I think we still have a couple things left to do in part two. For this bell-shaped population, as the sample size increases, what happens to our means? So my means were at 12.7, 12.9, 12.99, 13. Those stay roughly the same. Where's my green? Is for this bell-shaped oh wait, it's not bell-shaped anymore. Ah, this is annoying. Sorry. For this skewed population, all right, well, we got to change that. For this skewed population, as sample size increases, what happens to your standard deviation? My standard deviation went down from 10.5 all the way down to 1.5. So that is a huge drop, decreased significantly. And for this uh, skewed population, how does sample size appear to affect the shape? This is the exciting part. It is as sample size increases, the shape becomes oop, more normal. As sample size increases, the shape becomes more and more normal. Okay? Yeah, when we get to this part, Elaine, and like we discover this result, I always want people to like cheer and do the exciting faces, but no, everybody's like, "This is math, dude." So anyway,
Well, I get
whatever.
excited.
Yeah. Um, Basically, we're gonna use the fact that this is true for chapters 9, 10, and 11 to be able to continue to talk about the normal curve. So the rest of the class, we're going to be looking at means and standard deviations and normal curves and using that stat calculator's normal for the rest of the class. So because of this. All right, so part three. Part three is I said this project's very redundant. Part three is exactly the same as part two, except instead of skewed right, we're going to do skewed left. Okay. But the steps are very much the same. So just trying to hammer home the point. So we'll come back over here. All right. So we need to draw a population that is skewed left. So you're going to click and drag your mouse button again, make a big, huge tail on the left, a couple outliers out there, and big spike over here on the right so that its tail is off to the left, skewed left. You need to make sure your mean and your median are more than 2 apart. Again, I have 36 and 41. So those are a difference of 5. So I have a difference of 5.3. So mine's real skewed this time. I think the if you want it really skewed, make your big giant bar over here on the right a little thin, Okay. I think for when I was skewed right, I think mine was too thick, right? I don't think I want it like that. I think I want it real thin. Okay. Like that. Um, okay, so let's reset our sample size back to 2 and run that 1,000 times. And oh wait, I forgot to put in my mean and my median, right? So mean of the population was 36.18. Median was 41.48, and my standard deviation was 10.19. Round that up. Okay. All right. Run 1,000 samples, size 2, mean, standard deviation, shape. So now I'm using the mean down here, right? So I already clicked it. So 35.93 standard deviation, 7.14 shape. Very skewed left. Yeah. At this point, we've been doing this for 45 minutes. I'm sure you guys are like, all right, I can fill this out myself, right? 36.07.
I think they'd rather watch you do it too, though.
Watch me do it. Okay. Um, all right. I still think that mine is still very skewed left. Maybe yours is slightly skewed left. But as we all know now, as our sample size keeps getting bigger, it's going to get less and less skewed. So maybe, let's see, 36.19. I mean, you don't even need to watch me because you're not supposed to be putting in the same answers as me. So yeah. Well, the shape are going to have the same answers as me. So, all right. Lastly, for a sample size of 30. 30 is the magic number. Run it 1,000 times. Well, mine's still maybe a little skewed. That's okay. Um, it's because my original population, I made my original population skewed as heck. 1.91. We'll call this one normal. Okay. I will point out though that this population down here at the bottom, or this sorry, distribution of sample means, it's not a population. Distribution of sample means, I think this is still slightly skewed left. Okay. So I would have been better off if I kept going and got an even bigger sample size, where if I had 1,000, right? Now it's very normal. Or sorry, 100. Sorry, a sample size of 100 is better. Um, what would a what would a sample size of 1,000 look like? It's just basically just a single.
Not very interesting.
Well, no, but it's because the width of my histogram's too big. So, all right. Anyway, let's finish up this part 3. Um, for the bell shape population, your means going to stay roughly the same. Uh, Standard deviation decreases significantly. Now we've talked about the mean staying the same. Um, that makes sense. Okay, that as you take samples, your sample, sometimes you pick people that are higher, sometimes you end up picking people that are lower, right? It's random, but when you're picking your sample, usually you get a little bit of high, a little bit of low, and so when you average, it all lands right in the middle. Okay. um so that makes sense. We've talked about the shape, which is the part I'm excited about, but we haven't really talked about the standard deviation. Your standard deviation for your sample means, so this guy down here, let's go back to 30. The sample, sorry, the standard deviation that I had was 10.1, 10.2. Okay. But my standard deviation down here is definitely not that. Okay, your mean doesn't change. My mean's 36.18, 36.17. It's real close. Okay, but your standard deviation changes. And the reason why is because the standard deviation for a sample distribution is not called the standard deviation, it's called the standard error. And the formula for it is you take your standard deviation from your population, you divide by the square root of your sample size. So since you're dividing by your sample size, the bigger your sample size is, the smaller your standard error, the smaller your standard deviation will be. Okay. We will actually work on that formula. Uh, Not today, but on Thursday. Okay. So we'll take a look at that. Um, but that's why it's going down. As your sample size goes up, you're dividing by a bigger and bigger number. Okay. For this skewed population, how does the sample size appear to affect the shape? As the sample size increases, the shape gets closer to normal. Okay. Part four is just a recap of what we've done. Okay. Putting it all together for all population distribution types, whether it's skewed left, skewed right, it doesn't matter what your original population looked like. Your original population could actually look like a uniform distribution. A uniform distribution is where everything's the same height. Okay. And if you run this 1,000 times, your uh, sample distribution down here is still normal. Okay. You can make a roller coaster. Okay. Run this as long as your sample size is 30 or more. Okay. If you run this over and over and over, you end up with a normal distribution. Okay. So, for all population distribution types, how does increasing the sample size affect the sampling distribution of sample means? So, what stays the same, what changes, and how? Okay, so we're going to talk about the center, the spread, and the shape. As sample size increases, the mean stays the same. The spread, which is the standard deviation, decreases, and the shape gets closer to normal. Okay. That is it for our Chapter 8 project. Okay. So we're gonna click on share in the upper right, change our restriction to anyone with the link. All right, copy our link and jump back over to Canvas. Where did I put Canvas? There it is. I want to be in student view. All right, Chapter 8 project. Where are you? That's Chapter 7 project. Chapter 8 project. All right. We're gonna click on web URL, paste result, submit assignment, get our confetti. I got fire. No shamrocks today. Uh, and that's it. Okay. Make sure you watch your lecture notes. If you have questions, stick around. Everyone enjoy your St. Patrick's Day, and I will talk to you on Thursday. I'll probably be wearing something boring, so
Have a happy birthday for the rest of your day.
thanks.